describing the world as an Earth system scientist. Since then, I've listened to it several times, and every time I learned something new. In 2009, a group led with Steffen and Johan Rockström proposed the concept of planetary boundaries. Today, a well-known concept, which has great impact on sustainability work. And we'll introduce also a concept of Renaissance teams. The Renaissance person was a person who knew a lot about different areas. She or he could be an artist, as well as a scientist, as well as poet and engineer. Today the world is too complex for one person to be able to embrace all of what we need to know, which means that we need Renaissance teams consisting of persons from different disciplines and walks of life. And Will, you're a king of my Renaissance team, without knowing it. And our roads have crossed many times since then. And we are very happy that you are today an honorary advisor to our foundation. Carrie Facer, you contacted the Swedish Society for Nature Conservation, Naturskyddsföreningen, in Uppsala asking for us to meet. It was a surprise, a positive one, to be contacted by the Sandström Professor of Climate Change Leadership and a group that you reach out to society. We are looking forward to finding ways to how we can cooperate. We are not there yet, there are so many other things going on. I'm happy that Carrie is a climate expert involved in the more psychosocial aspects of climate change, including society, education, and the arts. Last weekend, we were presented to Biorelations in Uppsala, an afternoon that linked activities that explore the relationships between humans and non-humans in Uppsala. This is an ongoing exhibition at the Uppsala Art Museum. The known human-animal negotiating biorelations. It's worthwhile going there. This project is a collaboration with the Sandström Professorship in Climate Change Leadership and researchers from several disciplines. Well, without further ado, I give the word to Ingvar Rönnbäck, a moderator for the talk, founder and chair of ADF. Ingvar.
Thank you. I must say it's absolutely wonderful to see all these faces. We have two persons who will be providing us with an opportunity to talk, but you also come here with your histories. And I guess you are very curious. Maybe you have talked about Anthropocene and already have your views on it, I don't know. But it says that we have a challenging situation when it comes to how we live as a human species on this planet, of course. Maybe some words about another development foundation. We are in Uppsala now, but we have our headquarters in the city of Umeå, because it's the first, we call it as a think tank, do tank. And we have gathered with and other advisors. So we have a team of 20 international advisors, partners on 5 continents. And this is one of our activities, that we host these talks for various groups that we think would be having interest of. We're also working with international projects of different kinds. And myself, I'm coming from the peace and development background, looking at inequalities and conflicts as a source of environmental degradation. So that is a key part for me coming into this room. And I asked Ira and a friend of mine if you would like to join to be a member of the board for another development foundation. Maybe you heard about the concept before, I don't know. It's affiliated to what has been talked about in the Dag Hammarskjöld Foundation, and it has its history. I will not go into depth about that. Yeah, and we knew that Carrie would have this talk, and when she accepted to be a part of this conversation, she said, okay, I take the low profile and we give the floor to Will. And we thought that was an excellent way to have this talk by having Will to do a 30 minutes presentation of the Anthropocene, and then have a dialogue with Carrie, and then opening up for you. And we also have 30 minutes for coffee and tea. So you have the chance to talk with our eminent guests of this talk. So you're most welcome. I'm extremely happy to see so many faces. It was so many people that we almost didn't be able to squeeze everyone in, but we managed. So thank you. And now, Will, we're honored and we're very, very curious.
I think the first challenge of the Anthropocene is this computer, which is new to me. I'm a Macintosh user. So we get it up there. So there it comes.
Yes,
Yeah. That I think I can manage. So thanks very much, Ingvar and Ira, for inviting me to come here. And it's always fun to talk about the Anthropocene because this really is a Renaissance team concept in a way, because the term came out of the natural sciences community, but a lot of the discourse, very rich discourse around it, has been coming from all walks of life, inside and outside academia, the humanities scholars, social scientists, and all sorts of people. But I'm going to start my talk with the natural sciences, because that's where it came from. This photo comes from the student strike in Stockholm earlier this year, where the students remind us that we are bound up in all sorts of politics and cultures and so on. But there is a role for science to try to provide a background to what is happening to planet Earth. So the first thing to understand about the Anthropocene is already just the term concept challenge. The natural scientists, because we're very good at breaking down complex systems into ever smaller parts and studying them in detail. But the Anthropocene forces us to look at the Earth as a single system, which we call a Earth system. And this has origins in James Lovelock and Gaia and even scientists before then, but it's really taken off in the last 2 or 3 decades as a legitimate widespread area of science. So the Anthropocene has a geological sounding name to it, and indeed it has very strong geological connections. That requires us to understand planet Earth on long time scales. So the best way to start is this ice core data from Antarctica that was published about 2 decades ago now. And this is in hundreds of thousands of years. That's 400,000 years ago. And that red line is a proxy for temperature, what the Earth's temperature is doing. So I've put on here that human history can be mapped onto here because fully modern humans evolved about 200 to 250,000 years ago, and we've come through this last half of this record. But the interesting thing is you see a very regular pattern of short warm periods and long, rather erratic ice ages, about every 100,000 years. And of course that's typical of a complex single system that has its own planetary level properties. From our perspective, this last about 12,000 years of relatively stable warm period is really important for us, because that's the only time in which humans have developed agriculture and then more complex societies with villages, cities, and so on. We were hunter-gatherers everywhere before that, and in fact, we really didn't successfully get out of Africa until after the Eemian, the last interglacial period. So it's important to know that. So if we blow up the last 100,000 years, it looks like that. And you can see a little bit in more detail how erratic the ice age was, and then this relatively smooth, stable period of the Earth system for about 12,000 years. The geologists now have a name for that, or have had for quite a while now. It's called the Holocene. And what went before it, the ice ages and warm periods before it, is called the Pleistocene. And they singled this one out because it already has evidence of humans all the way back 10,000 years and so on. So it's an unusual interglacial because of humans from the very start. So why do we have to have another name, the Anthropocene? Why don't we just keep the Holocene as we go along? Well, the program I was working with back a couple of decades ago, which was headquartered in Stockholm, it was an international program called the IGVP. We were doing a synthesis about the year 2000, 2002, of what we learned about how Earth was changing and why it was changing. So what we wanted to do is capture humans, because we knew humans were important in the changes we were seeing. So these 12 graphs show, in a very, very simple way, what humans are all about. It's how many we are, it's what our economy is, it's urbanization, it's energy use, it's resource use, communications, and so on. So in a nutshell, that's what we humans do. And so we plotted these graphs from 1750, before the Industrial Revolution, because we thought the Industrial Revolution was important, up till originally 2000. These have been updated to 2010. Well, you can see the shape of those graphs. They're remarkable. The things were changing a little bit after the Industrial Revolution, but it was really the mid-20th century, 1950, when basically everything took off. And of course, there's some things that are more recent, like mobile technologies, which take off in the 1990s and so on. So we looked at that and said, that is remarkable how humanity has changed in just a couple of decades. So we really looked at that year 1950, and of course, being natural scientists, we said, can we see any evidence of this on the Earth? And so we did 12 graphs from the same time scale, 1750 to 2010. The top 6 of those 12 are what we call the geosphere, the non-living part of Earth. So it's the greenhouse gases, stratosphere. There's the climate system, surface temperature, ocean, and so on. The bottom 6 are the biosphere, the living part of Earth. So we have some things on ocean, coast, and land. And you can see, well, the Earth system is buffered, so it isn't perfectly the same sort of graphs. But again, we see a lot happening and a lot of change around 1950 and beyond. So we then dug into the literature for each of those in great detail, and we came up with 2 conclusions. One is that all of those 12 are outside of the Holocene envelope of variability. So we can go back in time and see how Earth is very naturally during the Holocene. But these are different now from the Holocene. They're directional, and their rate and magnitude is more than we see elsewhere in the Holocene. And the second thing we can say is this is not some natural swing in the Earth system. There's a massive evidence that say the primary driver of all these graphs are human activities of various types. So when we were discussing these graphs, actually before we put them together, but when we were discussing them in a meeting of this big international program called IGVP, this gentleman here, Paul Crutzen, he was the one who came up with the word the Anthropocene. So this comes from a meeting in February in the year 2000. The meeting was in Cuernavaca, Mexico, and the first publication was in the IGVP newsletter a couple of months later. And he then published a paper in Nature a couple of years after that. So Paul was an atmospheric chemist. He won a Nobel Prize for his work on the ozone hole, chemistry behind that. And he was really the one who said, particularly the paleoscientists, he said, stop talking about the Holocene. The Holocene is gone. We're not in it anymore. And then he first used the word the Anthropocene. Obviously, the sort of poster child of the Anthropocene is climate change. And so here's some of the most recent records of changes in global average surface temperature. And again, you can see from about the mid-20th century that there is a change in the rate at which climate is shifting. It certainly was shifting already early in the 20th century, but nothing like the post-1950 period. We're now about 1 to 1.1 degrees Celsius above the long-term Holocene average. But the interesting thing there is 1 degree or 1.1, 1.2 doesn't sound like too much. But the difference between an ice age, depth of an ice age, and the Holocene is about 4. It's only about 4 degrees. So this is already a quarter of the way. We're already committed at least to 1.5, and most of us think at least to 2. So we're really going into planetary terra incognita. And to give you an idea of what I'm really talking about here, there's a 2,000-year temperature record put together by Colin Summerhays at Cambridge. And Colin has estimated what natural variability looks like. So he's put the bound here. There's the green line is the mean average, and the blue lines are the bounds of variability. And this goes from 0, AD 0 to year 2000. So you can see the medieval warm period, so-called Little Ice Age. By the way, they do not show up on a global temperature record. Why? Because the Northern Hemisphere phenomenon. It was cooler in Australia during the medieval warm period. It had to do with ocean circulation, shifting heat from northern to southern hemisphere. So a lot of the skeptics say, oh, it was just as warm in the medieval warm period. And I look at them and say, you weren't in Australia, were you? It was cooler. So this is global average temperature, but this, put on the end of it, that is that 1 degree temperature rise that we've already observed. So you can see how dramatic that is, both in magnitude and in rate. That is way outside the bounds of the Holocene. Again, evidence that we're in the Anthropocene. So here's what the rates look like. The rate of atmospheric CO2 increase over the past couple of decades is about 100 times faster than when the Earth came out of the last glaciation. CO2 went from about 180 parts per million in an ice age to 280 in the Holocene. But that took about 7,000 years for 100 ppm. We've done over 100 ppm in a century and a half. It's remarkable. Global average surface temperature for half a century now is rising at about 170 times faster than the background rate, and in the opposite direction. This is why ecosystems are crashing all over the world, particularly around Australia. We've seen mass bleaching of the Great Barrier Reef. We've seen cockatoos fall dead out of the trees from heat, flying foxes falling dead out of the trees. It's because this rate of change is too fast. But the Anthropocene is more than the climate system. If anything, we've transformed the biosphere as much or more as we have climate. And a good simple way of looking at this is to look at the change in the biomass, the weight, the mass of terrestrial creatures with a backbone. So there you can see that. So it's everything that has a backbone lives on land. Mammals, amphibians, birds, and reptiles. So here we are. We humans are 30%. Just our body weight is 30% of the weight of all living creatures with a backbone on land. But our domesticates are another 67%. Cattle, pigs, chickens, etc. All wild creatures now only comprise 3% of the mass of animals on land. So that gives you an idea of just how dramatic the Anthropocene is. We totally dominate the land biosphere now. Well over half of the land biosphere is converted to human uses. There was a report that came out a few months ago by this very long name, this Intergovernmental Science Policy Platform on Biodiversity and so on, looking at the equivalent of the IPCC, looking at what's happening to the biosphere compared to the geosphere. And they came up with some pretty important statements. One is nature is declining globally at rates unprecedented in human history. That's a general statement, but they back it up with some more specific ones. The rate of species extinctions is accelerating, and some more detailed findings from that. The health of ecosystems, that is their functioning, on which we and all of the species depend, is deteriorating more rapidly than ever. We're eroding the foundations of economies, livelihoods, food security, and so on worldwide. In other words, we're living off the capital of the Earth. We're eroding the Earth's capital, not living off what it produces. Around 1 million animal and plant species are now threatened with extinction, many within decades. So if this trend continues, we are definitely going to see the 6th great extinction event in Earth history, probably within a century or two, the way the rates are going. And then the general statement there about how we are really diminishing and fraying the web of life on Earth. So it's an even more dramatic story, I think, than what's happening to the climate system. But of course they're related, because one of the drivers of this is a shifting climate. And of course deterioration of the biosphere affects the climate by eroding carbon sinks and so on. Well, the geologists have gotten into the act and put all of this together. There's a group called the Anthropocene Working Group. It's chaired by Jan Zalasiewicz from the University of Leicester in the UK. And there's 34 of us on this working group, and we've been working for a decade now. And we asked ourselves basically two fundamental questions. This is now from a geological point of view. Should the Anthropocene be formalized in the geological time scale? Right now, it's what we call an informal popular term. It is not a formal scientific term. So formally, we're still in the Holocene, and before that, the Pleistocene, and then you can go back to the Pliocene and the Eocene and Miocene, all those things you've probably seen on the geological charts. So we have to ask, is this thing real, geologically? And then should the base, or the beginning of the Anthropocene, the start date, be placed around the mid-20th century? Again, looking at the great acceleration graphs. So we've been working for a decade looking at cores already in the sediments, ice cores and so on. And we had a formal vote a couple of months ago, and it was remarkable. There's the formal vote. 29 to 4. I've never seen a consensus on such a complicated issue like that one before. So we had to have what was called a supermajority, which is 60%, and we got well over 80%. 29 to 4. That says, yes, this is real, this is geologically real, and we should use the mid-20th century as the start. That's phase one, so that's the first hurdle. The next hurdles are to come up with a core, supported by multiple other cores from around the world that reflect that, and then get it approved by the bodies above this core limit. That'll take a few more years, but we're working on cores. There are some of the possible indicators of the Anthropocene: aluminium, concrete, plastics, synthetic fibers. You could add radionuclides to that. You can add nitrates to that. You can add isotopes of hydrogen and oxygen, which reflect temperature change to that, and so on. So, and look at sweeping up from the 1950s. These are actual measurements of human usage of these materials, and of course they end up in the environment. And they are accreting in cores already that geologists can see. Well, the word Anthropocene, of course, refers to us humans. So that means that, as I said earlier, there's a rich, rich area of science in the natural sciences, in the geology, in the climatology, in the biology, and so on. But of course, we have to look at humans in our systems as part of the Anthropocene narrative. And we got a good reminder of this by two scientists from Lund, actually, who looked at the great acceleration graphs and said, you have lumped humanity all together, which we certainly did. They said you shouldn't do that because that masks what's really going on. So we went back, and for 10 of the 12 of our great acceleration graphs, we could, the human ones, we could break it up into three, and you can see those three shadings. The darkest orange is the OECD. That's the wealthy countries. So that's Europe, Australia, New Zealand, US, Canada, and Japan. The middle one are the emerging economies. So it's India, China, Russia, South Africa, so-called BRICS countries. And then the really light ones are the poor countries. And you can go through and see some really interesting patterns emerging there in terms of the different impacts of different human societies on the Anthropocene. But the two at the top, I think, are the most telling ones. In terms of population growth since the mid-20th century, virtually all of it has been in the BRICS countries and in the poorer countries, very little in the OECD. But when you look at real GDP, which is a really good indicator for consumption and pressure on the Earth system, it's dominated by the OECD, 75%. So these critics were right saying that you have missed the story by lumping all of humanity together. And they're right. So this is starting then the rich narrative of the human side of the Anthropocene. One of the things I think which really struck us too was some work by some British epidemiologists, Kate Pickett and Richard Wilkinson, who talked about income inequality and its impact. So we had to look at this. Let's look at the evolution of income inequality over about a century or so. And again, we're only going to look at the wealthy countries where overall income shouldn't be an issue. We are wealthy enough to have good lives. But what about the inequality? And what you see is interesting. In both English-speaking countries and in Europe and Japan, you see since the beginning of the First World War through the Depression, Second World War, very unequal societies got broken down and they became much more equal. So that was a common narrative of the first half of the 20th century. But then we see, really starting from about 1970 to 80, an incredible increase in inequality in the English-speaking world. The worst one by far is the United States. Australia is better off, but unfortunately we're going in the wrong direction too. But if you look at Europe and Japan, here you see a different story. It's more of an L-shaped curve of getting inequality down, and then around 1970, maintaining it at a reasonably constant level. In other words, not letting it drift back up like in the English-speaking world. Here's Sweden, down here in that yellow, if you want to look at Sweden. So you say, well, why does this matter? Everyone's pretty well off. Does it matter if there are a few wealthy people? Well, this is where the work of Pickett and Wilkinson is really important. I think this is an astounding piece of research, quite honestly. What they have done is taken income inequality in a country. So that's low inequalities, that's Japan, Sweden, Norway, and so on. There's high inequality, that's the English-speaking world. And they've just correlated it with social problems that are typical of wealthy countries. You can see what they are. They are not really due to poverty, they're due to other issues in these societies. But look at how strong the correlation is. I mean, this is a good correlation in the physical sciences. But in the social sciences, this is astounding. That there is a very strong correlation between income inequality over here and bad social outcomes. And the US is so bad it's off the chart. So they've got real problems they've got to deal with. So this is telling us that the human side of the Anthropocene, there's some extremely rich narratives and so on. But really what's happening at the base of all this are what I like to call system incompatibilities. We have a biophysical Earth system that's evolved over 4 billion years. It's evolved a terrestrial biosphere over 500 million years. It's been the home for humanity, and particularly the last 12,000 years have been an unusually good home for humanity. But that's changing rapidly. So what we're doing in the system is incompatible with the system's properties. Same with the biosphere, and of course same with the human sphere. We're seeing now growing instability in the human sphere. So, where are we actually going in the Anthropocene as we sit now, nearly at 2020? Well, let's go back then to our Earth system point of view and jump back a bit into the natural sciences. So that's that graph I showed you of how sharp the human influence is on climate today. But we now need to look at the future. And to do this, we need to use the climate models. I draw on the IPCC for that. So here are the so-called AR5, Fifth Assessment Report model projections. So basically what we're doing is using some assumptions about how humanity will develop and what technologies we use during the 21st century. And then we can have some plausible climate futures, very low emissions, very high emissions, one in between. And so these are fairly well known. You can see the temperature scale here, anywhere from, and this is actually not, this zero is not pre-industrial, by the way. I think it's 1980 to 2000 or something. So it's about 0.6 degree below, above pre-industrial. So we're talking here at about a 1.5 to 2, up to 4 or so, and one's in between. And people look at that and they say, well, yeah, that looks pretty interesting, but the curves don't look that bad, and it's only 2 degrees. How does that really matter? Well, you need to, again, look at this longer geological timescale view. There's the graph here. I've dropped out that little spike at the top. But what I want to do is go from 1900 to 2000. 2100 is about here. So let's put the IPCC projections on, and they look like that. So there you can see what this actually means in a 2,000-year perspective of what we're going to do with the Earth system. That's like a meteorite strike, basically, in terms of its effect. So it looks very different, and our challenge looks even much harder. My view is we are pretty much committed to nearly 2. I don't think we're going to make 1.5, certainly not given the present policy settings and what we know about the inertia in the Earth system. I think that's sort of a dreamtime story, as we say in Australia. 2 degrees possibly, but it's going to take a real transformation, and a pretty quick one. So, what happens when you go further up the track? A lot of us are saying between 4 and 5, the game's pretty much over. It's going to be hard to have a contemporary civilization that can cope, even with our modern technology, with a change that is that fast and is equivalent to the change between an ice age and a war period. That's a totally different Earth system. And it's so different that I don't even think the models come close yet to simulating what that's actually going to be like. So, the question is, how do we actually cope with this? And the kicker in all this is you say, well, if we don't make 2, maybe we can make 2.5. I think there's a growing concern, and I actually should pull this down a little bit now, I think, that these things called tipping points or tipping elements can be triggered, which essentially takes the Earth system out of our control and shifts it to a high state. This is a complex system framing, not a linear system framing, whereas working on the assumption that the Earth has well-defined states like warm periods and ice ages. And it doesn't stop in between. It oscillates between them, but it doesn't stop in between. So we're hypothesizing now that there's a risk that if we go much above the Paris targets, we're not going to stop till we hit the hothouse of something much hotter. We know what these tipping points look like, or at least some of them. You can map them on in terms of melting of ice, erosion of biosphere, circulation changes, and so on. I won't go through them in detail. just to say we already see them being destabilized. There's the Amazon. We've had 3 droughts, 2005, 2010, another one in 2015-16. It's eroded carbon storage. We can measure that already. Permafrost, we're starting to lose some permafrost. Carbon, a very small rate at the moment, but that would be highly nonlinear. Arctic sea ice, that's probably crossed the tipping point. That will almost surely be ice-free in another decade or 2. Coral reefs, that's probably crossed the tipping point. I think we are now doomed in terms of having the Great Barrier Reef. It'll be gone at 1.5, and I think 1.5 will be there in a decade or 2. Greenland, that's interesting. When I started out in this business, everyone thought Greenland was stable till 4 or 5. Now people are talking about 1.5 to 2 in terms of tipping that. That's 7 meters of sea level rise. West Antarctica, there actually are now scientists coming out saying we may have tipped it already. We may be over the tipping point. And the problem is these things are probably linked in terms of cascades. They're connected obviously by temperature. If you emit carbon from the